All right, let's jump right in. I want you to do something for me. Just for a second, close your eyes and try to picture, well, nothing. Absolute, total emptiness. You're probably imagining a big black void, right? Like an empty stage where things can happen. But what if I told you that stage, that very idea of empty space, is a complete illusion?
And that quote right there, that's the heart of what we're digging into. The nothing you think you see between the stars, or even between the atoms right here in your own hand. It's not only something, it might just be the most important something in the entire universe.
Ah, yes. That is the million-dollar question, isn't it? And the answer, I promise you, is going to completely flip how you see reality. It's a story that involves invisible arrows, the deep secrets of light, and, yeah, the mind-bending ideas of Albert Einstein.
To even begin to get our heads around this, we need a new mental model. So I want you to throw out that idea of the empty box. From this moment on, I want you to think of the entire universe as a giant cosmic block of jello.
This is the absolute key. Space itself has physical properties. It's a medium. So, physics isn't just about the stuff floating around in our cosmic jello. It's about describing the wobbles, the strains, and the stresses of the jello itself.
Okay, so how in the world do we describe what's happening at every single point in this massive jello? Well, for that, we need a new language. And that language is the language of fields. It's how physicists literally draw a map of reality.
Let's start with the easy one, a scalar field. Just imagine a block of metal that's, say, hot on one end and cold on the other. Every single point inside that block has a specific temperature, right? Just a single number. That map of all those numbers, that's a scalar field. That's it. Simple as that.
Now here's where it gets really interesting. What happens when you add direction into the mix? Think about a river. At any given point, the water doesn't just have a speed, that's a number. It also has a direction. It's flowing somewhere. A map of all those tiny invisible arrows, each with its own length and its own direction, now that is a vector field.
And this lays out the difference perfectly. A scalar field just tells you how much at every point, like temperature. But a vector field tells you how much and which way, like the wind. One's a map of numbers, the other's a map of arrows.
And to speak this language of fields fluently, you only need three basic verbs, if you will: gradient, curl, and divergence. The gradient tells you the steepness, the quickest way up the hill. Curl measures the swirliness. Think of a leaf getting caught in a little whirlpool. And divergence measures how much something is spreading out, like water from a spray nozzle, or flowing in, like water going down a drain. Believe it or not, these three ideas can describe almost all of physics.
Okay, so now let's put this new language to the test. We're going to use it to solve one of the weirdest and oldest mysteries in physics, magnetism.
Seriously? Think about this for a second. Gravity? It pulls you straight down. An electric charge? It pulls you closer or pushes you away. Nice and simple. But a magnetic field? It shoves you sideways, perpendicular to the direction you're moving. It's just bizarre. Why does it do that?
The answer, and this is so cool, comes straight from Einstein. So from your point of view, standing in the lab, it's pretty simple. You see the current in the wire, that current creates a magnetic field, and that magnetic field pushes the other charge. Easy. But now, let's do something wild. Let's shrink down and ride along with that moving charge. From its perspective, it's not moving relative to the current, so there is no current, which means there should be no magnetic field. So what the heck is pushing it? Well, this is where special relativity kicks in. Because of its motion, space itself actually contracts. The space between the positive ions and the wire squishes together, making them look denser. All of a sudden, from the charge's point of view, the wire looks positively charged and it gets pushed away by a plain old electric force.
So get this, the crucial point is, what one person sees and calls a magnetic field, another person, just by moving at a different speed, experiences as an electric field. They are not two different things. They are two faces of the exact same coin, linked together by the weird, wonderful geometry of space-time.
And all of this brings us right back to our cosmic block of jello. We've seen that space is a medium, that it's filled with these fields, but the reality is actually even stranger. The vacuum of space doesn't just behave like jello, it behaves like a solid object.
I mean, let that sink in. This is a massive idea. Empty space is not some passive, empty background. It has measurable physical properties, just like a block of steel or a piece of glass.
Think about it like this. If you whack a block of steel, a sound wave travels through it, right? The speed of that sound wave depends on two things: how stiff the steel is and how dense it is. Well, it turns out that when you whack the vacuum, say by wiggling an electric charge, a wave travels through it too. We just call that wave light, and its speed is determined by the stiffness and density of the vacuum itself.
And I want to be clear, these aren't just cute analogies. Those weird constants you might remember from physics class, permittivity and permeability, those are the real-world elastic properties of empty space. One of them, permittivity, is basically a measure of how much the vacuum resists being polarized by an electric field. You can think of it as its electrical stiffness. The other, permeability, measures how it responds to a magnetic field. That's kind of like its magnetic density.
So if the vacuum is a solid, does it have a breaking point? Let's look at something simple, like a piece of chalk. If you just pull it apart, that's called tension. It snaps pretty much straight across. But if you twist it, that's a force called shear. Something really weird happens. It breaks in a perfect 45-degree spiral. Why the difference?
The math behind it reveals a hidden secret. A pure twisting force, a shear, actually creates a line of maximum tension that's hidden at a 45-degree angle. The chalk is really weak when it comes to tension, so it finds that hidden line and just breaks right along it. The way something fails tells you everything about the hidden stresses inside it.
And this brings us to the most mind-blowing conclusion of all. If you apply an electric field that is powerful enough, if you pull on the fabric of space hard enough, the vacuum itself will snap. It will tear apart. And from that pure stress, from literally nothing, an electron and a positron will pop into existence. The vacuum breaks, and matter is the result. So, the space between things, it isn't empty. It's a solid, elastic medium, and it's buzzing with potential. It can store energy, and it can be stressed until it literally breaks and creates the very particles that make up our world. It really makes you wonder, what other fundamental truths are hiding in plain sight, just waiting for us to look at them in a new way?